Chapter 4 switches gears and begins talking about water. Water is fundamental to weather. If we did not have water in the atmosphere, we would not have weather as we know it. So it's important to get a fundamental understanding of water and how we measure it, how we talk about it, and how we generally understand, get a general understanding of water in the atmosphere before we really need to get into all the very technical and very meaty stuff of weather. So let's begin that discussion. There is always water in the air. Even in the driest places on Earth, there's just a little bit of water in the air. The thing is, the water in the air is a gas. It's water vapor. So we need to start talking about water vapor. The first thing to realize is we can feel it, and it affects how we feel, and we can have a sense of how much water vapor is in the air by how it feels. But realize that we can't actually see water vapor. Water vapor is invisible. If you see something that looks like water in the air, and do not be tricked, it is not water vapor. If you can see it and it is made of water, you are looking at a liquid. For example, if you see clouds, that is not water vapor. That is liquid water suspended in the air. As it turns out, even though there's water vapor everywhere, even in the driest places, it turns out the atmosphere can't hold just any old amount of water. There's actually a certain amount it can hold, and the amount it holds is called saturation, or when we're talking about a total amount it can hold. Once it's full, it is saturated. So it turns out that the amount of water vapor the atmosphere can hold, or when it becomes saturated, is actually heavily dependent upon its temperature. So before I jump too far into that, let's back up. What does it mean when we're talking about saturation? Well, we're talking about how much the atmosphere can hold. So let's say this little mini mason jar is the atmosphere, and it is devoid of any water at the moment. So our atmosphere is pretty dry. When I put more water vapor into the atmosphere, it starts to fill up. Okay, I am starting to get more moist. The atmosphere is starting to get more moist. The amount of humidity in the air is increasing. Okay, I'm getting pretty close to the top here. If I add more water vapor into the atmosphere, my cup is now full. The atmosphere is saturated. It is holding as much water vapor as it possibly can. What happens if I add just a little bit more water? Well, if I add just a little bit more water, it is going to overflow. Okay, the little bit that's coming over the top, you could consider, it's kind of a small analogy for things like condensation. The condensation results when the atmosphere can't hold any more water vapor, and in those situations, the water vapor condenses into liquid water and falls out of the atmosphere. Now, understanding that what saturation is, it's dependent upon two main things. We can become saturated in the atmosphere by, one, decreasing the temperature. If I decrease the temperature, I'm effectively decreasing the size of this glass because I can hold less. So if I keep the amount of water in there constant, and let's say I cut the glass off right here, there's a whole bunch of water up here that now falls out of the glass, and there's one way that I can get things like dew to form by dropping the temperature or reducing the amount of water vapor the atmosphere can hold. The other way, of course, is by pumping more water vapor into the atmosphere, basically pouring more water into the glass. It turns out the atmosphere is much more effective at cooling off and reaching saturation that way. Chapter 4 discusses quite a few different ways to talk about how much humidity or how much water vapor is in the air. There's really only three main ways that you need to really concern yourself with. They are the dew point temperature, relative humidity, and mixing ratio. Dew point temperature tells you the temperature that you have to cool the atmosphere down to in order to reach saturation. So it's kind of it's an absolute measure of how much water vapor is in the air, because it tells you how much you have to decrease the size of your glass until water spills out. Mixing ratio is a little more technical term. It tells you the absolute mass of the air, or a mass of the air versus the mass of water vapor in the air. So that is an absolute measure of how much water vapor is in the air. The last one is relative humidity. And relative humidity is a relative term, and I'm going to talk about that in just a second. But understand, it is not an absolute measurement of water vapor in the air. It is absolutely dependent on temperature. And because it is absolutely dependent on temperature, it tells you nothing about the actual content of the water vapor in the air. It does tell you how sticky or how moist the atmosphere can feel. That is true. But as an absolute measurement, no way. Only dew point and mixing ratio are the ways to go. Let's talk about relative humidity for a little bit. This is a sticking point for a lot of people, and it needs to be clarified at the beginning here. So when I say humidity, just as a single word, I'm just talking generically about water vapor in the air. When I say relative humidity, I am talking about a completely different thing. Here's why. I have said, and if you haven't read yet, you will read about the atmosphere's ability to hold water being totally dependent upon temperature. When the atmosphere is warmer, it can hold more water vapor than when it's colder. So think about it this way: that little mason jar that I showed you becomes bigger when the atmosphere is warmer, and becomes smaller when the atmosphere is colder. So I've got other bottles here. The small bottle is when the atmosphere is cold, and the warm bottle is when the atmosphere is warm. Okay, so the warm one is bigger, the cold one is smaller. Okay, you see the size difference. Alright, that being said, I have drawn lines on here that are labeled. So you see 50% here, and then you can see 50% on this bottle. If you notice, both bottles, shake the water a little bit, both bottles are precisely halfway full, or both are 50% full. If I put them side by side though, the warm atmosphere has got slightly more total water content inside of it. Okay, they're both half full, but because the warmer bottle is bigger to start with, the atmosphere, in this case, the warm one, actually holds more water vapor in it. But this is why relative humidity gets very confusing, because it's based off of temperature. Because relative humidity is based off of temperature, it is possible to have more water vapor in the desert, where the relative humidity may be 10%, than in the, say, the North Pole, where it's extremely cold, but the relative humidity might be 95%. Alright, it's the return of sensible weather. Sensible heat, sensible weather, how you feel, is largely dependent upon how much water vapor is in the air. This is where the heat index comes from. The heat index is based off of completely how the human body feels, based off of how much absolute humidity, or how much water vapor is in the air. In cases where it's very hot and very humid, the human body will sweat, but the sweat cannot evaporate. Because sweat evaporating is a cooling process for the body no longer can cool off. And that's where the heat index comes in. It's the feels like temperature, because your body starts to feel like it's getting much warmer because it can no longer cool off. Hence, sensible temperature, the heat index is a sensible temperature even. A question I get asked a lot is, why do we need relative humidity if it's so confusing? Or why do we need dew point if we've got relative humidity? Well, the answer is complicated, because it depends on which situation and what you're trying to do and what you're trying to find out. Dew point is a really good, what's called operational measurement to use for things like low temperature. A dew point is usually, or can be, a very good prediction of low temperature, because once the temperature reaches the dew point, condensation occurs and latent heat is released, and that keeps the temperature from cooling off too much more at night. Relative humidity is important because it tells you how close you are to saturation at a given temperature. And if you're very close to 100% relative humidity, being saturated, then you're much closer to either having dew or fog or frost, or in the above the ground, a cloud. And in those circumstances, relative humidity is important in calculating the probability or the chances of getting a cloud, or at the surface, fog. So when to use each one is kind of a relative term, or a relative question. I will say dew point is more valuable in an everyday forecasting scheme because dew point gives you an indication of the absolute moisture content of the air, which is important for things like thunderstorm development. So that aside, both are equally important when we talk about saturation, because relative humidity tells you how close you are to saturation, and dew point tells you how much in a relative, non-mass terms, it gives you an idea of how much water vapor is actually in the air. So both are valuable. The saturation, obviously very important for cloud cover. We need clouds only form when the air becomes saturated and the water vapor in the air condenses out, falls out of the cup, so to speak. So using that understanding, how do we reach saturation? Well, if you remember the relative humidity examples, cold and warm, one way to increase the relative humidity is actually just decrease the cup size, right? And you decrease the cup size by decreasing the temperature. So that is the most important way to reach saturation, is decreasing the temperature. How do we decrease the temperature? Well, just by going up in height, since the atmosphere decreases with temperature with height. How about that, right? The other way, of course, is to just increase the absolute content of water vapor in the air. That is a little bit more difficult, but it does happen in certain circumstances. So that's how you get cloud development, and that's how everything I've talked about otherwise in terms of water relates to that. Going beyond that, Chapter 4 talks about cloud types. It goes into extreme detail in cloud types. That's great if you want to be a taxonomist of clouds, but you don't need to be that for this class. There's really three basic ones that you need to know. It's cumulus, stratus, and cirrus. Okay, cirrus are high levels, stratus are blankets, cumulus are cotton balls. And that's really what you need to know. It does talk about clouds with development, but that falls under cumulus. Cumulus clouds can be cotton balls that start to grow and grow and grow, and those are your thunderstorms. So there's just three: cumulus, cirrus, stratus. Whatever order you'd like to memorize them in, those are the important ones to keep in mind. By all means, learn the other technical types if you'd like. Everything that comes on is just a combination of those three names, or the nimbus, which is just a verb meaning it's raining, or alto, which is just middle. So that in mind, that's kind of a quick and dirty of the water chapter in Chapter 4. So good luck in the remainder of the week, and I'll talk to you later.